in the communication for that. We would like to have 4 board members going forward. The Concrete Society of Southern Africa is a non-profit company. It's up and running, and it needs members, dedicated members, to keep it going. And please, if there's anybody considering that, don't hesitate and put your name forward or nominate somebody who you think is relevant. And we will check if they accept the nomination, and then we take it from there. These are the membership fees. Thank you to our current members. The sessions I'm looking forward to in August. That will be I'm sure you get the correspondence. Those are the dates. And also the concrete class, 14th of August is the next one. We have our normal branch activities. Look out for the communication. And then for the CDP points, last time my slide wasn't fixed, thanks Natasha, to get the arrows in the right place and not overlapping. So that has been tidied up. Then Professor Alexander, I think we all know Professor Alexander, and we welcome you, Mark, to present to us, and we look forward to hear what you say, and I'm sure there'll be the odd question coming up, because I think this is new technology, and it's exciting from my perspective where I sit. So thank you, Mark, and over to you.
Thank you, Mark. I need to share my screen, which I will do once you leave. Yeah, there we go. Okay,
it's my that's right. I've left.
Yeah, I have it. Thank you. All right, so there we go. Just want to make sure that everybody can see that. Is that correct? Okay, am I audible and am I visible? I mean, my slides. Can I have a...
All good. There's a few thumbs up, Mark. It's okay. All yours. It's all yours.
All right, good. Well, welcome everybody to this CONCRETEfiX program webinar. The topic is up there: low carbon binders and concretes with a view to their durability and adoption in construction practice. Quite a big title, but anyway. I do acknowledge my colleagues and students, most of whom really do the work. So it's good to acknowledge them, mostly members of the Concrete Materials and Structural Integrity Research Unit at UCT. First of all, I just wanted to congratulate the Concrete Society on the Fulton Awards dinner of about a month ago, the event. I came up to that, and I was absolutely delighted to see a crowd of close on 270 people. And what particularly delighted me was that I knew so few of them. Now, why do I say that? Well, it just means that that there's a whole lot of new faces, renewed interest, and that was very encouraging to see. And if you're not a member of the Concrete Society, I'd really strongly encourage you to sign up and become a member and make the society as great as it needs to be. Also, if I can just mention that what I'm going to be sharing this afternoon to a large extent is what I presented just a few weeks ago at a similar type of conference on low carbon cements in Switzerland. And so I've kind of borrowed these slides to present today. I hope that they'll be of interest. So let's get started. Let me see if I can get started. There we go. Okay, so this is what I want to cover: an introduction, resources, some motivation and background, low carbon binders, what are they, what do they mean, durability concerns that may relates to these newer binders, and then some standards and policies that need to move us to that point where they can be adopted in construction practice, and then we'll bring it to an end. Now, these are some very interesting slides here, and I am obliged to Franco Zanino of UC Berkeley for these. If we look at the resources that we use in construction, and we look at those three diagrams on the left, the one is a mass diagram, mass of materials. The second one is a volume of materials. And the third one is the fossil or the CO2 emissions for all these materials. And these materials are from wood in the top or timber right down to concrete in the bottom. And it's quite clear that in terms of mass and volume, concrete occupies the greatest amount of material that we use. And the reason is that we use so much of it. That's the big issue with concrete. And you can see, obviously, if you look at volume, timber occupies a much larger slice because of its low density. But when you start to look at the CO2 emissions, the picture immediately changes, and steel jumps right to the top of the pile, as you can see there, in terms of the CO2 emissions from the steel. So the CO2 emission per kilogram of steel is very high. And concrete takes a lower profile here. And I think that's an important point, that although we use this material in such huge quantities, its overall contribution, while very significant and needs to be brought down, and that's why we're talking about these issues, is less than you might expect. And that's contrary to what many opinions are out there in the popular or press, or in the let's say, the uneducated press, if I may put it that way. So in terms of our use of this material, you can see there also that 90% of all the materials that we use on the face of the earth are related to construction. So we're in an industry that has an incredible impact on the overall sustainability, let's say, of the planet. And 75% of that is concrete. So you can say around about 3/4 of all the materials that are used on the planet relate to cement-based materials. So it's huge, and that's the kind of industry we're involved in. If you also look at, let me try and get this here. If we were to replace just 25% of concrete with timber sustainably, this would require new forests about 1.5 times the size of India. So people are talking about timber as an alternative material. It has a niche, of course, but it's not going to replace concrete in the foreseeable future. Here's another very interesting slide. Here we have the global building floor area, or the floor area per continent or per region, which is expected to double by 2060. So look at the picture here. We've got the Americas, we've got Europe, Asia, and Africa. And it's quite clear that it's in places like Africa and parts of Asia that we're going to have to build like mad. There's a huge amount of material that has to be provided, floor area, new buildings, and everything that goes with that, including infrastructure. And so this question of construction and building new facilities is a huge issue, a great challenge, and how we're going to do that while at the same time starting to minimize our carbon footprint. Those are the real challenges that are going to face us moving into the future. And that's a very interesting slide. Here's another one, the question of the use of cement-based materials on the basis of availability and reactivity. If we look at the availability of cement-based materials, now we're switching over to these materials now, you can see that in terms of, if we go further down here to the cement, let me just find a pointer here. There we go. If we look at cement, of course, we're making a lot of it, over 4 billion tons, although that's starting to come down, with China now cutting back significantly. With the other materials here, rice husk ash, silica fume, burnt shale, natural pozzolan, slag, fly ash, and so on, relatively small quantities. I think with the fly ash, we've got quite a lot in South Africa, so this graph doesn't reflect that, a reserve. But with the clays and the limestones, the calcined clays and limestones, in effect, we've got, I wouldn't say unlimited, of course, but substantial resources of these materials that are available to us in construction. And this is where we probably need to be focusing our attention. Also on the reactivity side, if you look here, you see that, let's say fly ash, a typical material that we use, with this bound water here at gram per 100 grams of the paste, sits here at around about 5 of those units. Natural pozzolans, similar. Slag, about double that. And then the clays. The clays, as you can see here, are really superb materials. They have double the reactivity of, for example, fly ash, and even better than silica fume. So these are materials that really deserve our attention. Now, let's just go on. There we go. Another one here is the distribution of kaolinitic clays, the 1-to-1 clays. The montmorillonites are 2-to-1 clays. And again, one can see that these are distributed all over the planet. More particularly with our own continent, they're well distributed in East Africa and Central Africa, less so in South Africa, but for us who sit in the Western Cape, there's a really good couple of sources down here, and other parts of the country also have good sources. These represent the desert areas, the Kalahari and the dry Karoo. So we've got lots of clay. There's plenty of that all over the world, South America, to lesser extent in India, but there is clay, abundant clay resources pretty much everywhere we need it, particularly in Africa. And that needs to be contrasted with the availability of limestone. And if you have a look here, this is not a good slide. I apologize for the legibility of it, but around here, around the Mediterranean Sea, there's lots of limestone. We know that the whole Mediterranean basin is based on limestone. So you get lots of it all over here. But in Africa, limestone is actually a relatively scarce material. Got some here in Uganda. There are deposits, of course, in pretty much every country, but not large deposits as to carry us way into the future, which is where we need to be. For example, Tanzania doesn't have anything showing here. We have our own resources in South Africa, including down in Cape Town. But if you compare that with that previous slide, we've got clay and we have limited amounts of limestone. And here we're talking about cement grade limestone, the sort of limestone that we can use to make cement, which is usually a high grade limestone. And that is getting into increasingly short supply and is a concern for the future. Now, let's get back to the topic in hand, which is this question of low carbon binders. And I've got some definitions here. First of all, the durability definition is an important one. Durability is the ability of a structure or a component to withstand the design environment over the design life without undue loss of serviceability or a need for major repair. Now, that's important because durability is not an intrinsic material property. You cannot talk about durability of concrete without talking about its environment and it's the life for which you want it to operate. So what might be durable in one environment, concrete that's durable there, may not be durable in another environment, and one must not confuse that. So durability relates that to that concept of material performance. It's not a purely intrinsic property, and relates to the dominant deterioration mechanism. On the other hand, if we look at what low carbon binders, what those are defined, I've made up this definition. I think it's not bad. Binders with significantly lower carbon footprint than traditional PC or Portland cement, achieved via use of supplementary cementitious materials, including these calcined clay materials and other alternative binders, and possibly the alkali activated materials, which may have a niche, but quite a limited one. And the caveat here is that any material that we are contemplating here as a low carbon binder must have a total lower carbon footprint in the finished product. It's no good doing that on a limited basis. One has to look at the whole picture before you'd make your mind up. That's very important. Okay. Now, we're also talking here about the low carbon economy and circular construction. Up till now, we're used to this sort of loop here where we get the raw material extraction. It's really a linear diagram, but for the sake of space, shown in this way. We then go and make our construction materials. We construct infrastructure, buildings, and so on. We use them. We then deconstruct or demolish, goes into construction and demolition waste, and normally to landfill. However, we have to move into this loop here. We have to go into the complete loop where we bring it in, we begin to reuse these materials either as new aggregates or possibly sources for cement or some other use where they're not simply disposed of. And that brings us, of course, to the idea of the circular economy, which is a multi-level resource use system that stipulates a complete closure of all resource loops. Recycling and other means that optimize the scale and direction of resource flows contributes to that circular economy and its supporting practices and activities. In its conceptual perfect form, all resource loops will be fully closed. In its realistic imperfect form, some use of virgin resources is inevitable. That's where we're trying to move at the moment. Now, to step back a little bit, actually, low carbon binders are not new. We've been using slag cements in South Africa for certainly more than half a century, from the 1950s, actually, when a lot of work was done at the NBRI of the old CSIR and Mills at Wits University and others. And if you look at this diagram here on the right from Fulton's Concrete Technology 1969 edition, I think it was the fourth edition, you can see that we have Portland blast furnace cement there, and that would have been roughly a 50-50 cement with clinker and blast furnace. So we've been using this stuff for quite a long time, and in many cases at highly extended values, for example, some of our dams, and we've got to understand its properties pretty well. And it's in many cases shown admirable durability. Of course, in some cases not, but mostly it has. So what I'm saying here is that concrete is in reality a low carbon material. I'm going back a little bit here. These are the numbers that maybe should have come up earlier. So let's move on from there. But for the novel binders, these newer materials with which we're now starting to work and try and understand, essential information is needed on their properties and use. Another point, and this is more of a worldwide phenomenon, that the slags and fly ashes are slowly being phased out in the medium term. In South Africa, we have a large supply of fly ash in our ash dams. And I think that's a source of SCM that can be well utilized into the foreseeable future. But we're going to have to learn how to beneficiate that material. And in some cases, we don't have that because in the Cape, we have no fly ash whatsoever produced in the thermal stations. So here are some key questions that might prompt our thinking. First one is, what are the essential challenges in getting new information and applications of low carbon cements or concretes into practice? What are those challenges? Secondly, what actions do we need to take in those areas? And then thirdly, what will be the effect of climate change? Higher temperatures, lower relative humidities, greater rates of deterioration. How can we understand these looking into the future? These are some very key questions. And some of the suggested pathways that I would like to propose here are as follows. First of all, the importance of fundamental research. If we don't understand the materials we're working with, we can't use them effectively. Fundamental research has to be done to understand them properly. Then we also need to carry out work on concrete, not just pastes and mortars. This conference I attended, I mentioned a few weeks ago, we spent 4 days talking about cements and very fancy ones, 1 day talking about concrete. It should have been the other way around. 4 days on concrete, 1 day on cement, because it's concrete that's the real engineering material. Cement is not an engineering material. It's used to make an engineering material. And so we've got to carry out work on concrete. And importantly, we must have field applications, demonstration projects that prove the viability of the systems, because engineers need real sort of data to back up what they have to use. We also need policies and standards, materials and construction specifications, appropriate standard test methods. These are great challenges moving forward, and we continue to need academic and industrial collaborations to move this whole thing forward. Now, what durability issues might be expected with low carbon binders and concretes? Well, first of all, many people will say rapid carbonation. Well, yes, but I want to make the point that I don't think that that is per se a durability problem, and I'll come back to that. Then there are microstructural changes with time, for example, from the ingress of aggressive agents, effective environment, changes of phase assemblages within the paste, and so on. Then there are issues where alkalinity residual is essential, for example, in carbonation and soft water attack, where we need a certain amount of alkalinity there. Early strength issues remain a major challenge in any of these systems, or many of them. and also the fact that in many cases they're not yet robust enough to be used in construction. One of the great successes of Portland cement concrete is its robustness. We abuse it, we use it in all kinds of ways, we sometimes get it all wrong, and somehow it always seems to come back and do the job for us. And that's because it's a robust system, and that's what we need in construction, is robustness. Durability also requires both chemical and physical durability. So we need to understand chemistry and physics, particularly in relation to transport properties. On the physical side, we need impenetrability or tightness of the microstructure. And microstructure can change with aging and things like carbonation. And then on the chemical side, we need adequate hydration products, interactions with those products with various aggressive agents, the buffering aspects for carbon dioxide and chlorides, the alkalinity issues, the lower Portlandite or calcium hydroxide residuals, the soft water attack, and the sulfates, and so on. And then there's always a competition between these two aspects, which has to be understood. Right, so here we have the system as a whole. This is a big picture here taken from Fulton's, the latest Fulton's concrete technology. We have to think about the concrete system and the exposure system. And as you can see, there are a multiplicity of factors. This is not a simple problem. We have intrinsic factors on the concrete side, things we sort of know and understand, binder type, binder content, water binder ratio, and so on and so forth. Extrinsic factors, that would be largely the process and production parameters. And then on the exposure side, physical and chemical attack. We need to understand the kinds of deterioration mechanisms that are at play when important deterioration mechanisms are present. And how do we handle that in terms of adequate durability? So concrete durability sort of fits into that central slice there where it comes together between the concrete system and the exposure system, and we have to bring both of those to bear on the problem. Also, with many of these newer cements that are starting to be looked at, the point that needs to be made here is that, of course, anything new has no history of performance. That's a big issue. Performance sort of history. And the problem, therefore, is that the early age and some of the later reactions in these newer low-carbon cements have long-term consequences at the engineering and structural level. And very often we lack that data and have to sort of project into the future on the basis of quite limited short-term data. This is also a challenge. Now, it's actually corrosion of the reinforced concrete structures that is the overriding concern. If we look at that diagram on the right, it's a well-known diagram where we see that we have rebar covered by the covercrete, and on the outside of the concrete structure, we have drying, certainly in the early stages after construction and loss of moisture. We have a curing affected zone, which is relatively small. And then we get right from the beginning the ingress of aggressive agents, whether it's chlorides, water, carbon dioxide, or oxygen. And that cover concrete, which is typically 30 millimeters or maybe 50 at the most, is what protects that structure for its entire design life against corrosion. So we're not concerned about the bulk concrete, we're concerned about the cover concrete. And just like the skin analogy, the skin of our bodies is what protects us and gives us longevity of life. It's that cover, the skin of concrete, that gives it the life that we want. And that's where we have to understand what's going on. And hence the whole durability index approach was based on that philosophy. And if we think about corrosion, we don't want this kind of thing to happen. The Morandi Bridge in Genoa in 2018, which came down, that collapse of that very interesting structure, which was pushing the boundaries at the time that it was built in the 1960s. And it was a bold design. And what happened there was we just didn't have enough redundancy in the system, that when corrosion finally took that structure down, there weren't alternative load paths for that structure to remain standing. That's a structural engineer's nightmare, and we don't want that to happen, of course. And in PC systems, with regard to corrosion, generally, this is again why plain Portland cement systems have done so well, because we've got this high alkalinity reserve, which admittedly can be depleted. We have, on the other hand, it has limited binding abilities for particularly chlorides. and it has a low resistivity, but in general, it does quite well. In low carbon systems, now we're talking about systems with clinker contents of, let's say, 60% and lower, so quite extended cementitious systems. They may be less robust. This question of robustness comes up again, more sensitive to processing techniques, temperature, and so on. On the other hand, they may offer better resistance to aggressive ions, and generally they have a lower alkalinity, which can be an advantage in the case of AAR, for example, but sometimes also a disadvantage. So those are things we need to be looking at. And this is the big picture that the engineer and the building owner or the structural owner always has to have in mind. The whole design life, the whole life scenario, where initially we have this construction and we have this initiation period. This is when the nasties are getting into the concrete, and this is where we need to be spending our money, here in this time, not here. This curve does this. It's a schematic in terms of the level of damage, but the cost curve is orders of magnitude higher than this, and it goes up much faster. And we're finding this out to our detriment in South Africa, where we haven't maintained our infrastructure. And now to fix it is almost impossible in some cases. And replacement costs orders of magnitude more than had we fixed it at this stage and taken care of our structure. For any building owners and structural owners, infrastructure, take care of your structure here. Don't wait for it to get here, because all of this can happen. And what sort of limit states are we concerned about? Mostly at the present time with durability and particularly reinforcement corrosion, we're looking at an initiation limit state. This is where we're designing to. But we need to be thinking about, can we design to these other limit states? This is obviously a bit too far, but can we work in the propagation period? Because many of our structures are sitting in this region now. Can we continue to extend their lives? These are the big questions. Now, looking at some local data, the first diagram on the left there is in fact from Fulton's 10th edition. And I think this was about a 40 millimeter cover, but we've got time to chloride-induced corrosion with a series of binders. First of all, a CEM1, plain cement, a fly ash at 30% and a slag at, say, 50%, and the water binder ratios. And you can see quite clearly here that with the plain Portlands, the plain cements, that in fact, this says maybe 10 years of corrosion-free life. Well, there's going to be a lot of variability here, but you can see that it's really quite low. The other materials, the blended binders, these are low carbon binders, maybe the 30% fly ash, not entirely yet, but you can see the huge benefit. And the reason for that is quite simple, that if we look at the long-term apparent diffusion coefficient, that's this parameter here, dA, at 20-year value, the diffusion coefficients in these blast furnace and fly ash concretes are so low compared with plain cement here. So these reduce incredibly with time. The microstructure is improved actually to such an extent that we get this huge improvement and hence a much, much longer life. And that's true for all the different marine zones within which we might, with which we might be concerned. However, that's not the whole picture, because it's very, when you come to do site work and you start to try and take actual site measurements of chloride profiles. Chloride profiles from the lab are beautifully ordered, nice sort of Fickian curves, but on site, the story is very different. And here's work from my colleague Hans Boyshausen, where he looked at a whole lot of things around the coast, Port Nolloth, Walvis Bay, Cape Town, different zones, different years. And what you see is chloride profiles that seem to be sort of going all over the place. And so the traditional chloride profile is not quite so easy to find in real structures. And these are samples taken from very close to each other. So they're not from vastly disparate structures. They're from relatively closely spaced or closely sampled sites within these structures in hand. So the variability is huge. And that's something we have to, again, grapple with. So there's the lack of correspondence between the real site data and the lab data. Easy to work in the lab, much more difficult on site. Very high variability, even when different samples are tested from the same or neighboring elements. And based on that scatter, can we really do reliable chloride prediction? Well, impossible, very difficult. It's a question. And what are the limitations of chloride ingress modeling? I'm not saying we shouldn't be doing it, but we need to treat it with respect, and we need to have a little bit of humility when we start to look at the models that we use for chloride ingress. Now, talking about carbonation, that's the other issue that frequently causes reinforcement corrosion. Here in PC systems, plain cement systems, before carbonation, we have that high alkalinity residual, which is a buffer against CO2 ingress. After carbonation, actually, calcium carbonate precipitates in the pore space, porosity reduction and pore refinement may occur, depends on the water-cement ratio. So in fact, carbonation here is not a threat. It can in many ways be an advantage. It improves the concrete. It turns a thermodynamically unstable material, meaning portlandite, into a thermodynamically stable material, meaning calcium carbonate. So that's an important fact. However, in low carbon systems, before carbonation, actually these are pretty good materials. Lower critical and threshold pore diameters, there's a refined pore structure, and so on. But after carbonation, the question is out here, the jury is still out, the question of coarsened pore structure, higher connectivity, reduced interaction of transport media with pore surfaces. What are these effects? Well, let's have a look. Here's some very interesting work coming out of some work at IIT Delhi under Shashank Bishnoi, where they took fully carbonated mortars at 3% CO2, accelerated carbonation testing. Here are the parameters of the test, the environment of the test. Bear in mind that these are fully carbonated, and we're looking at resistivity in kiloohm centimeters. On the left here, non-carbonated, on the right, carbonated. And look at the scales. Resistivity here up to 150 kiloohm centimeters, on the right 25. And here you can see that the Portland cements or the plain cements are down at the bottom here, less than 20, often only 10 kiloohm centimeters. Hence, they're not very resistive, and therefore corrosion can occur. The other materials, this in particular here, this is a slag, PS there. It's an Indian material, really superb. And even the calcined clays are doing really well. Carbonate those materials in mortars at least, and under accelerated conditions, the whole picture turns around. Now the Portlands are doing much better. They've improved, plain cements, but the other materials have not. So the resistivity has come down, and you might say, well, does that threaten the long-term durability? Well, maybe or maybe not. Here's some very different data coming out of our own work, which Kilomelia is doing at the moment in Dar es Salaam under our supervision at UCT. He's looking at PC and low carbon systems and resistivity of carbonated and uncarbonated binders. He's looking at limestone calcined clay cements. This is the clay he's using, and different grades of limestone down to 59%. This would be a non-cement grade limestone. This would be a cement grade limestone. And we're looking at these lower grade limestones, unsheltered versus sheltered. And that's what happens. So here, the natural carbonation, this is 6 months. It's only 6 months, so it's very limited. We're waiting for the 12-month results. And here we got the SEM1s and 3 calcined clay systems. And here you can clearly see that they're carbonating faster. Unsheltered, a little bit slower than in the sheltered, as we know, because of the presence here of moisture in the environment. As far as resistivity is concerned, in fact, Menard Kilomeli finds that at least at 6 months, who knows what happens, we'll see in 12 months shortly. In fact, his concretes in the unsheltered are improving with resistivity. We're back at 150 kiloohm centimeters, which is really very good, really excellent. In the unsheltered, I beg your pardon, in the sheltered, it's going somewhat in the other direction. But this is not a problem, because here, corrosion is not going to be an issue because it's sheltered. In the unsheltered, that's where the corrosion is an issue, and looks like, in fact, if anything, the resistivity may be improving. We need long-term data, and this is the importance of doing real site work, real long-term work on actual concretes and not relying purely on lab-based approaches. So this is really interesting data, and it seems to contradict to a large extent some of the accelerated data that is coming out. This is also work that was done on kaolinitic clays from Tanzania. There's some superb clays up there. And you can see here, this is Portland cement and slag concretes. Way down here, less than 200 kiloohm centimeters. But even that, at 100, these materials are still superb. Well, a previous student of mine, Emmanuel Leo, was measuring these kinds of values. Actually, I asked him, do you really believe those values? And I don't know if I do believe them. They were measured in our own lab with our own equipment, and I'm still not sure that I believe them. But whether they're true or not, the fact is that these clays have got incredibly high resistivities, which means that corrosion may not be a problem in the future. Here's another very interesting set of data. Carbonation data. This dates back quite a while to some work done in 2006 on essentially sandrail structures, bridges, that we got some data from. And here we've got the depth of carbonation versus age. And this is Cape Peninsula for a range of concretes, all of them pretty well plain Portland cement concrete. And you can see that, in fact, in this case, very few data are exceeding about 30 millimeters of carbonation, a couple of outliers. But overall, it's sort of clustering down here. First of all, the typical carbonation rate curve is not very clear there at all. And secondly, the carbonation depths are not terribly high. So is that a factor that we need to take into account? Admittedly, this is for plain Portland. If you look at the Johannesburg area, again, unsheltered, and we've got 30 and 35 grade concretes here, lesser time frame. But even here, carbonation is hardly exceeding 30 millimeters within the time here. Look, in the case of the Cape, we've got 18 years of data there. In the case of Johannesburg, 30, mainly from the Johannesburg motorways. And here again, maybe carbonation is not the huge issue we thought it might be. It may well be so, of course, in the low carbon binders, but then we've already had caveats in regard to that matter. So Rylam, in a very recent Rylam letter in June 2025, had Rylam TC281, which is around carbonation, had this to say. In the review that is in this report, it is reported that there are many cases from engineering practice where carbonation of the cementitious matrix surrounding the steel do not lead to noticeable corrosion or to corrosion-related damage at the level of the structure. Go and read that report if you want to see some more. Right, we need to bring this thing into land as soon as possible now. Let's talk briefly about standards and policy, because we need to get these newer materials into the construction space. And that is easier said than done. Bear in mind that engineers work to codes of practice and specifications. They don't work to research data. So we have to turn the research data into usable codes of practice. And that's not something that researchers like to do. And may I mention this huge issue here. If appropriate standards are absent, including new specifications and codes of practice, uptake will be limited and sketchy. And we stand in serious danger right now in the country as a whole, that our standards are not being updated because the old CCSA has now closed down, and that was a body that was tasked with having to update standards. Brian Perry has done fantastic work there over years, and that is simply hanging in the air now. So if the industry doesn't take it seriously to make sure that our standards are updated, and this is largely an industry issue, it's not an academic issue. The industry has to push the updating of appropriate standards, otherwise our industry will ultimately grind to a halt. That's an extremely important point, if I may make it. We need also to move from prescriptive to performance-based specifications, because prescriptive specs that we currently largely have simply cannot handle the complexity of the new developments into which we are moving. And the prescriptive approaches are there, and they have their limitations. I've mentioned them there on the left-hand side of that slide. There's no possibility for rational design. We cannot incorporate new materials here because they're not covered. Also, the site data often doesn't show correlation with intentions, pretty well like we saw earlier. And here we have research running well ahead of practical implementation. We've got lots of research data coming out, but we have very little practical implementation, largely because of this gap in our standards and our codes. The move to performance-based specifications is gathering momentum. I'll talk a bit more about that just now. But the performance-based approach is given here. You have to quantify your environmental loads and the deterioration mechanisms. You must have performance criteria, prediction models, means of considering variability, and appropriate specifications and QA systems. And the picture is it's a whole picture here. We've got the owner, the design consultant, the material specifications, the concrete producer, the material properties, the contractor, all of which should lead, if it's done properly, to durable concrete structures over there. So it's a whole picture sort of approach. And in addition to codes of practice, we also need some policies where, for example, we start to talk about having to produce materials with low carbon footprints, or even setting standards on those carbon footprints at national, regional, and international levels. Doug Hooton from the University of Toronto stresses the problem here is the lack of knowledge of performance specifications, including the parameters and tests we need, lack of appropriate specifications themselves, and the important role of the importance of defining the roles of the different performers or the different actors within the construction space, and the need for demonstration projects. Now, where are we in regard to that continuum, if you like? Well, at present, the current EN 206, which is SANS 50206, I think, does not include explicit performance parameters or tests, so that doesn't really help. FIB, the Model Code 2020, which has now been adopted, toys with these aspects, but doesn't really grapple with them to the point where we can use some of these things effectively. Performance-based specifications do, however, exist. The CSA, the Canadian Standards Association, particularly with regard to chlorides, is a very eminently suitable specification for them, at least. We have our own COTO spec, which picks up a lot of these issues. There's a French program here that's picking up on some of these issues. We've got some interesting work coming out of China, and the Swiss one based on the Torrent meter, which is also in place. We now fortunately have a Portland calcined clay limestone cement standard that has just been produced in India, 2023. That's really helpful. If you get hold of that, you will see how they're working with this material. So we actually have a standard in place for this particular material if we need it. We could base ours on that if we wanted to. And in ASTM, Americans are moving ahead. Should I say, North Americans are moving ahead with this kind of ASTM C595. Right. So let me bring this to a conclusion. I've been long enough already. Low carbon cements and concretes have been used successfully. They're not really new, but some of the newer binders are going to need a lot of work to really understand them and verify them in practice, to the point where we can be reasonably confident in their long-term performance. We need that indeed. Service life models for these newer materials are useful, but they're unlikely to be any more accurate than the existing models, which, as we saw, do have limitations. We still need fundamental research, including the production of these cements. But at the same time, we need real field data. We need a comprehensive suite of performance specifications, ditto rate policies and regulations. And in many cases, durability issues such as carbonation may be able to be mitigated by suitable structural design and mix selection. So I think we've got a very exciting field ahead of us. Lots of work can be done, and I'm sure that the space will change rapidly in the years to come. To close, let me just bring to you two quotes. The first one is from Corin Scrivener at EPFL in Lausanne. This is what Corin has to say. Making cement is simple. Well, some of our cement people may want to contest that remark. Nevertheless, making cement is simple. Making cement simple is very difficult. In other words, these new cements need a lot of understanding, and making them simple is not that easy. I want to finish off with a quote from Sandy Fulton. Making good quality concrete is not difficult, but making good quality concrete consistently is very difficult, with associated challenges for low carbon system. I hope that might stimulate your thinking. So with that, let me bring this to a close and thank you for your attention. And I'm sure if there's some questions, we'll do our best to answer them. Thank you.
Thank you, Mark. That is, it's nice to see a global perspective on these things. Sit back and look at the big global perspective, and the use of steel and timber and all that. It does put it into perspective. I'm not sure if I must look at the comments page. If there's any. Are there any questions at this stage?
I'm trying to look for that as well, Mark.
Yeah, for some reason I don't see coming up there.
Okay. Yeah.
Natasha, am I missing something here?
I don't see any questions either.
I actually had a thought or a question, I guess, because many years ago there was that high luminous cement which looked like it had potential and started being used. And then there was I think it was called conversion. Mark, maybe you can help me, where they said, okay, here's some long-term problems with high luminous cement. We cannot use it in structures because of the conversion. Now, if you start introducing calcined clays to such large percentages, 60% of your mix in that, I'm sure that's been sorted out, but maybe there's just a little bit of background information there.
Yeah, good question, Mark. Yeah, the high aluminum cement story dates back to the 60s and 70s in the UK, where they had a collapse of a number of post-tensioned or pre-stressed beams in high humidity and temperature, relatively high humidity temperature environments, for example, indoor swimming pools, where the material was shown to, with time, the semi-stable hydrates converted to stable hydrates, which increased the porosity of the system enormously and resulted in a major loss in strength, and hence they had these collapses. It's a well-known fact that calcium aluminate cements do this, but we can overcome that through appropriate mix design. They didn't understand that in those days. Appropriate use of or choice of water cement ratio. You do get different grades of calcium aluminate cement. The high aluminum cement is what we used to call it. And so even with conversion, you can still use these materials adequately, but of course the cost is a big issue. So where they get used is largely in things like corrosion control in concrete sewers, where they can be used as sort of coating layers, 20 or 30 millimeter thickness, where the cost can be justified, and where they exhibit much greater durability to sewer gases and so on, if that helps.
Yeah, so I guess time will tell if we find any new long-term effects in certain environments. Yeah.
I don't know if my slides are still showing, but anyway.
Yeah, we can see you. We can still see your slideshow there, Mark.
Okay, because when you're finished, I want to come. Maybe I can just put the slide up quickly, and the current slide, just to bring this to the attention of our audience this afternoon, that in February next year in Cape Town, we're very privileged to host the next international conference on calcined clays for sustainable concrete, 4th to the 6th of February 2026. We'll be at the Graduate School of Business at UCT down on the waterfront. Everybody likes to go to the waterfront. So we'd love to have you there, either to make a contribution. I think it's not quite too late to make a contribution if you want to submit an abstract. There is a website there, and certainly if not, to come along and hear some of the latest on the use of these materials, I think would be very helpful. Thanks, Mark.
Yeah. No, thanks. I like that photo, by the way. It's a really good photo.
Yeah, it is a lovely photo.
I think, Natasha, if there's nothing forthcoming here, if there are no questions or comments, then we are close to 4 o'clock. There's a comment from Belinda. I think we saw that.
Yeah, she says, please share this event to our members.
Yeah.
Natasha, can you get that? I sent you the slides. Can you send that on? I think it's already been advertised through Concrete Society. Maybe it just needs another one.
Yes, I've been dealing with Hans
with Hans on this one.
Yeah. So we've been advertising it on LinkedIn, and we've sent out mailers to our members before. Right. And then Belinda, to answer your question, if Mark's okay, I'll share his presentation slide on our website.
Yeah, that's fine, no problem.
Okay, perfect.
Yeah.
Matthew, I also load the recording on the website, so it will be available soon there.
Okay, awesome. Thank you, Natasha.
Pleasure.
And thank you, Mark,
think,
for the insightful webinar.
Yep. Thank you. Thank you, Mark. I think hand clapping of hands is certainly appropriate. And there's nothing else we can call it a day. There's a question there. Your microphone, your mic is off. Or was that not a question? No.
It wasn't a question. Do apologize. And
Sorry.
thanks, Mark. Very, very insightful.
Thank you. Thanks for your comment.
Thank you very much, and enjoy the rest of the afternoon.
Thank you.
Thank you, everybody. Thank you, Mark, for your
Thank you,
your
Mark.
time
Thank
and
you,
your
Mark.
expertise.
Thanks, everybody.
Pleasure.
Bye.
Keep well.
Bye.